Okay, so real quick, what's my problem-solving method that I want to use for this type of a problem, where I have 30 grams of copper pellets are removed from a 300 degrees Celsius oven and immediately dropped into 80 milliliters of water at 25 degrees Celsius. Okay, so there's some equations that I know that I can use, because basically what we're asked for here is what's the final temperature that this system is going to reach. Okay, so first we have to think about things that could cause it to reach a final temperature. Heating or cooling, conversely, that's one example, or a phase change. Now, this is the problem-solving process we have to step through is there a phase change occurring for a situation like this? No, we don't think so. It's unlikely, because the copper pellets are going to be dropped into the water. But we can't assume necessarily that there won't be a phase change, so we have to keep that idea open as a possibility. But what we do know is there's definitely going to be a heat transfer going on in this situation. And the heat transfer is going to go from the copper pellets to the water, and they're going to reach a common temperature. So our equation that we want to use is Q equals mc delta T. And then we're going to have two of these equations, one for the copper pellets and the mass of copper, and the other for the water. So I'm going to have Q1 MC1 M1 C1 delta T, and then we're going to have Q2 equals M2 C2 delta T, where this is the mass of the water, and then this is the specific heat of the water. And then we know that this heat is going to be transferred between the system. But here's a really easy place to make a mistake. If you just say Q1 equals Q2, you're going to get the wrong answer. And why is that? Because it's not true. Because actually, Q total equals 0. So Q1 plus Q2 equals 0. So Q1 equals minus Q2. So you have to set that equation up correctly to get the right answer. So that's important. These specific heat problems are tricky. You have to remember the total heat in the system is conserved. And once you make that step, you won't get this problem wrong anymore. That's like a little problem-solving piece of information there for that type of problem on the homework, in case anybody got stuck on that one. And that's true for, yes? So what you would do to tell if it goes through a phase change or not is you figure out the final temperature that this thing comes to. And if it comes to a temperature where there's more heat left over than there is to keep it, in other words, if the temperature of the water at the end is bigger than 100 degrees Celsius, then you know that actually a phase change is going to occur too, probably. Because once it gets over 100 degrees Celsius, that the temperature change is going to be so much so that there's also going to be a phase change, and some of the water, if not all of it, will vaporize and go into a phase change there. And that's a more complicated situation. But that's totally reasonable to solve for a problem as well. So that's a great question, and that's how you know. You have to sort of calculate what these Q's are, and you have to figure out, okay, what's my final temperature? And then, okay, wait a second, maybe I actually have to do a third step where I have the phase change involved as well. And how would that work? Here's how it would work. You'd calculate the heat that goes into warming up the water. And then you'd figure out how much heat how much capacity there is for these copper pellets to heat up the water to a certain amount. So that would be the first calculation. If that amount of heat gets you over 100 degrees, then you have to go back and you have to calculate the term, and you have to say, then you know what T final is. You know T final is 100 degrees for this term with the water, because you know it's going to start with whatever it started with and stop at 100. And then you're going to write a third equation. You're going to have Q3 equals mL, where L is the latent heat of vaporization for water. And M is the mass of water. Great. And that's how you're going to do it for problems like that where there is a phase change involved. Definitely practice those. Have you done some of those in your discussion section? Practice versions of that? Yes. Yes. Okay, great. That's why it's so important to go to discussion section, because you're going to get more practice with these kinds of problems, so that it seems simple, right? But when you actually do the application, it's not so simple. So it's very important to make sure that you know how to do all of that, because if you get that sign change wrong, it's going to be very confusing, which is very easy to do. Okay, great. So now that we've gone over that point, I want to jump back into this work and heat transfer with gases. So we talked about how gas can do work, or work can be done on a gas, because we have this pressure and there's a force going on because we have a pressure across an area. So there's a force and a displacement. If a piston, the height of the volume of the gas changes by the piston height going up or down, there's a displacement there. So there's a work that can be done, dx, where dx is the height of that piston. So we can see that. Get an eraser really quick. So we have this piston that can change some height here, and then the gas is inside. So here's the gas particles, and then it can, if it gets displacement here, dx, it can go up and it can do work, or it can have work done on it and have it pushed down further. And in one case, the force is going this way in the same direction as displacement. And since work is force dotted with dx, there's a dot product there that's implicit in that definition here, where dx is my displacement, delta x. In one case, the work is going in the force is going in the same direction. When the gas expands, the force is going this way, the pressure is going outwards, and there's going to be a displacement this way too. So they're in the same direction, so we can say that the work is positive. And in the other case, if I take this and I press it inwards, my force is going in a different direction. And then I have to sort of define this direction, this dx, to always be going in this direction. So in this case, the dx is always going to be, the x-axis is defined this way, so we define the dx to be negative. So we can have is minus, and then we have negative work being done. But you could define it the other way. You could say, well, I'm calling it positive if dx goes this way, and then these signs change. So depending upon the convention that's used, work can be positive or negative. But for the same system, one of them's got to be positive and one of them's got to be negative. Which one you define to be positive or negative depends on the textbook. There is no universally agreed upon rule for that, because both of those are equally valid ways of viewing the system. So just keep that in mind. But we define it to be one thing for this particular book. So here they're making a decision here. So stick with the sign convention used by the book. So the sign convention, here we have that the gas pushes with force, pressure going this way. And then there's an external force in place to keep the piston. And so it should be equal and opposite. Whoops, let's see here. Equal and opposite here. So that's one example. And then we have displacement. As the piston moves dx, the external force does work on the gas. So in this case, the external force is doing work on the gas, and the volume changes by dV is equal to A dx as the piston moves dx. So the piston is moving some distance here, dx. Okay, so then we can apply this definition to calculate the work done when the volume of a gas changes. So here we see the gas pressure in this figure here. It shows that the pressure P with the volume can be changed by moving the piston. And the system is the gas inside the cylinder, which exerts a force of magnitude, pressure times area, on the left side of the piston. So the gas is exerting, in this picture here, it'd be going this way, pressure times area, where this is my area here, pi r squared equals the area. Okay? And then that's on the left side, and then to prevent the pressure from blowing the piston out of the cylinder, there must be an equal but opposite external force pushing on the right side of the piston. So using this coordinate system, F external is equal to minus the force of the gas is equal to minus pressure times area. Okay. So then we see here, now let's say the piston moves a small distance dx. As it does so, the external force, which is the environment, it does work. It does work. Force external dx is equal to minus PA dx. So here we have that minus sign introduced for the work. And then if dx is positive for the expanding gas, then the work done is negative. And this is to be expected because the force is opposite the displacement. If dW is positive, if the gas is slightly compressed. So depending upon whether it's expanding or compressing, in one case the work is going to be negative, and in the other case the work is going to be positive if dx is less than 0. So if the piston moves dx, the gas volume changes by dV is equal to A dx, and then the work done, dW, is minus P dV. And if we allow this gas to change slowly from an initial volume to a final volume, the total work done by the environment is found by integrating this equation here. So we just count up. For our purposes, we're going to have typically a constant pressure and a constant area. The only integral you'll have to do is like the dx part, which is just like the amount that it goes up or down. So you just count that. So the integral is really easy. It's just a length, essentially. Okay, and there we have it. The pressure volume work on a gas is given by that negative sign, from volume final to volume initial, P dV. So when is it positive, negative, or 0? Work is greater than 0 when the gas is compressed. The volume decreases and the energy is transferred. So this convention actually chooses it to be this one. So the work is positive when we're compressing it. Okay? So that's the choice made by the book. The volume decreases and the energy is transferred from the environment to the gas. And we say that the work is done on the gas. So work is done on the gas, and it's positive when the work is done on the gas. Basically, the analogous thing is I do work on this eraser, and I give it new energy. It has higher gravitational potential energy here than it does when it starts off at the floor. I do work on the eraser. Then there's work done that's negative to bring the eraser back down. That's the other side of this. So when work is less than 0 is when the gas expands. The volume increases and the energy is transferred from the gas to the environment. And we say that, so that's the key thing, energy transfer. We define it as a volume increase and energy transferred from the gas to the environment. That's when work is negative, when the gas is losing energy. So always remember that, and you won't get this wrong when you get the sign convention. So we can say that work is done by the gas, but that's an indication that the work in the first law is negative. So that's our sign convention. And then it's 0 in a constant volume process. So the pressure and temperature can change, but no work can be done unless the volume changes. So if this height just stays the same the whole time, no change, no work is done. Okay, so then in a constant pressure process, which we often have, we can take P outside the integral, and we just have the integral of P dV. And if my area is constant here, which it always is for a piston, this simplifies further, because then dV, integral dV just becomes area taken outside the integral. It's pi r squared, but none of that changes. And then integral of dx from 0 to L, a dx. And that's my volume. And then that total gives me my volume. So that's where that comes from. Okay, so the subscript P indicates that the work done as pressure is held constant. Delta V is V final minus V initial. That's the volume change. Delta V is positive if the gas expands, so the work done is negative. Delta V is negative if the gas is compressed, which makes the work positive. And then we can also have a constant temperature process. And then we have a situation that's a little bit more complicated. So for a constant temperature process, we need to know the pressure as a function of volume before we can integrate equation 12.31. So this is the kind of thing that when the scientists were doing experiments, they got a little bit confused about this, because this one's not so simple. We have to go back to our equation of state, because we could have a changing pressure, and we could have something that's changing here, and we have to come up with our equation of state to figure it out, because now we have just a constant temperature process. So we go back to our old equation for work that we had before in the earlier slide for work done on a gas, but then we have to do a little bit of calculus to do an integral. So let's see how they get that. So this part is the same, but we put a subscript to denote that it's a constant temperature process. And then it's going to be equal to minus the integral of from V initial to V final. Notice that the integral is still over V, because if it's not, then there's no work done. Volume has to change for work to be done. And then I have P dV. But now I have to go back to my definition of P and what it meant in my ideal gas equation. So we have PV equals nRT, right? And then we have to solve for P in terms of V. So we divide by V, and we have P equals nRT over V. Now let's take this over and substitute it into here. So we have minus, we have our integral. Instead of P, though, instead of it just being P, now it's this function. So now it's nRT divided by V, and then we still have this dV on top. Okay? But we said that it's an isothermal process, which means that it's a constant temperature. And we're going to assume that the number of moles of the substance doesn't change either. And R is a constant, so nRT can just come out front because it's a constant. And then I have this integral of dV over V. And the integral, we remember this from calculus, of dx over x is natural log of x. So this integral turns into minus nR t natural log of V. And that's how they get that. Okay? So there we go. So we have, for a constant temperature process, we have work done at constant temperature is equal to minus nRT, integral from V initial to V final, natural log of V. And then we have to take that integral between the limits. So I have to do, limits. And we had V initial to V final. So we have V final to V initial. And then what we find then is we have minus nRT, and then it's natural log V final minus natural log V initial, by the definition of how we take the limits of an integral. So we have minus nRT, natural log V final, minus, and then it's minus nRT natural log V initial. And so then you can just factor that out, and you can write it as a fraction here by my rules of natural log. So I have minus nRT natural log V final over V initial. And that's how I get that final expression there. Okay. So, any questions about how I got that formula? Okay, great. So let's see. There's definitely some great problems in the homework that you're going to put this to use. I recommend working those. Get a lot of practice. You could expect to see some of that stuff on the first midterm. And if you have any questions, of course, you're welcome to come to office hours, and definitely go to discussions. Have you done any problems with finding work done by a gas in discussion yet? No. Okay, great. So I'll send an email out, and we'll get that taken care of next week for sure, so that you have practice with that for the midterm. Okay, so we're going to change topics a little bit, but that's related to what we just did. So we've talked about ideal gases, and we've talked about work done by a gas, how we can write an equation of state, how the pressure can change if the volume and the temperature change, how these three variables all go into this ideal gas equation. Actually, it's 4 variables because n can be a variable. A lot of times it isn't, but it can be. And then R is the constant that relates all those 4 variables. But we didn't talk about something that's really important to thermodynamics and statistical mechanics in general, that sort of explains what's really going on behind the scenes, which is entropy. So I'm going to give kind of a lengthy discussion on entropy because it's so important to so many different fields of science. And you're just going to hear entropy coming up whenever you watch like science shows and things like that. It comes into play. A lot of times people think of entropy as how organized or disorganized the system is. And what we're going to see is that that's only true in some cases, and that's not really a precise definition of what entropy is. But what entropy is it's something that emerges when systems interact. And it basically explains why heat is transferred to begin with. Like, why do we even have this process of heat transfer? Because we said, okay, if you have one object that's hot and one object that's cold, heat gets exchanged between them and their environment, and it just happens automatically, magically. And we have these math rules that explain how to calculate it. But that's great. It's good to have a rule to calculate something, but it's even better if not only that we have a rule to explain how it happens, but then we have an equation that explains why it happens. That's what we really like in physics. We want to know, why is this the case? That's more satisfying than just being able to calculate it. Entropy explains why. And the concept of entropy is so important that it has many practical applications. You'll see applications to chemistry, data science, AI, information theory, statistics, computer science, machine learning, physics, biological systems, biophysics, and more, many more. So this is just an example from computer science. We have a decision tree where we have to figure out, the decision has to be made by a computer where to draw the dividing line. And here we have a low entropy system. So this does tie into that idea about organization versus disorganization entropy. You see that a computer science class will define that very often to be the case, because for their applications, that's often how it breaks down. But here we can see that for this low entropy decision, the decision for how to split the data is very simple, but for this higher entropy system, it's way more complicated. And then we're going to be dealing with entropy, though, applied to the physical sciences case. So we're going to talk about reversible versus irreversible processes. It turns out that understanding entropy is the key to understanding why so many physical processes in nature only go in one direction, like why two objects reach the same temperature, but they don't go back to being two different temperatures. It only goes one direction. Think about that. That's pretty weird. Well, the explanation as to why is because of entropy. It's an irreversible process. Like an ice cube melting. It melts, but it never freezes back into the same shape it was once before. Maybe it melts and then the room gets cold again, so it refreezes. But it doesn't refreeze into that same shape. It just refreezes into whatever random shape it's in after it melted. So we say the process of the ice cube melting and losing its characteristic shape is irreversible. Another example is the mixing of chemicals. You can take two chemicals and mix them together, and they start off separate, but they diffuse and they merge to be roughly consistent throughout. And that process doesn't go in reverse, typically. It only goes in one direction. But going in reverse would not violate energy conservation, which is one of our fundamental principles in physics. So there's got to be something else at play besides energy conservation. There's some other law of nature preventing these processes from being reversible. And this is where we're going to talk about the second law of thermodynamics. And this is the law that explains reversible versus irreversible processes. We studied phase changes and we learned that they are reversible, and that is true. But why is only part of the process reversible? Only the part where the water molecules themselves refreeze. The phase change part is reversible, but the back into the shape that it was in is irreversible. So why is that the case? So the key to understanding irreversible processes is to make the connection that the irreversible part is a macroscopic feature of the system, while the reversible process is microscopic. So in the case of the ice cube, the macroscopic state of the ice cube is all of the ice cube water molecules stacked up into the particular crystal structure that makes them into that ice cube shape. That's a macroscopic property of the system. But the reversible part is the microscopic part, where each individual molecule of ice can turn into liquid, but it can turn back into ice again. So the microscopic part is actually reversible, and the macroscopic change is irreversible. Okay. And then, in other words, the individual molecular processes, such as the phase change from water molecule to ice molecule, or the chemical reaction causing the two chemicals to mix, is reversible on the individual interaction scale from molecule to molecule. But in each case, some thermal energy is exchanged in the system, and each molecule interacting does obey conservation of energy. But the total arrangement of all of this system contains more information than just the thermal energy of the system. It also contains information like what's the position of this molecule with respect to this molecule. And all of that information about specific positions and momentums of particles and who has what specific bit and how those are arranged, that ties into entropy and what really explains what entropy is. So let's understand that better by taking this simplified model. So we're going to approximate an interaction between molecules in a system as a simple elastic collision, just like we did for gases in a container. They're colliding elastically and sharing momentum. So an elastic collision would be like the molecules in the gas bouncing around, sharing momentum, and they interact. In an inelastic case would be where they actually interact chemically to change their potential energy. So if they interacted inelastically, it'd be like an oxygen molecule colliding with another oxygen molecule, and they also formed a new bond and become O2. We're going to ignore that for the time being, but it also is important for the second law. It's not just these kinetic terms where they bounce into each other that matters. The potential energy terms do matter as well. But we'll start by looking at just the elastic collisions. So we've got A and B. Both of these gases have the same thermal energy. But we have a different situation. Oh, and also we did skip kinetic theory from the last chapter, but there's one important concept from there that you need. The thermal energy, which is the same as the thermal energy from the first law of thermodynamics, is the kinetic energy of all the moving atoms and molecules. So the only thing that you have to know to understand entropy from kinetic theory, because it is based off of kinetic theory, but the only, really, for our purposes, the only thing you need to know is that the energy that I have from my motion is kinetic, and it's connected to momentum. So all of the entropy that I have in a system, it has to do with how my energies are distributed across my particles. So if I have gas molecules and they're in some container and they have some entropy associated with them. Let's say I have like 4 particles. And I say that the energies of these two systems are the same, but the total energy of this one is equal to this one. So we'll call it E1 and E2. But the entropy is not the same. And which one has higher entropy depends on this. So kinetic theory is 1/2 mv squared equals kinetic energy. And there's another way that you can write kinetic energy besides 1/2 mv squared. You can also write it as p squared over 2m. And that's a more useful way to see kinetic energy from the purposes of what we're doing here. Now, how do I get that? What is P? Momentum. That's mv. P is a vector, m is a scalar, v is a vector. So we have a sensible thing. So we have p squared over 2m, but p squared is mv. So I can say, okay, mv, so I have m squared, v squared over 2m, but then look, one of my m's cancels out, and I'm back to mv squared 2, or 1/2 mv squared. So that's how you can see that these two expressions are equal. And why is this more useful? Because with this arrangement, the idea with kinetic theory is I have a system of particles, in this case a gas. Each gas molecule has a different momentum and a different position associated with it. Okay? And in this case, I'm going to say that my first molecule contains all the energy, and it's going to be equal to 4 joules of energy. And these ones have no energy associated with them, which means they're not moving. P2, P3, and P4 are 0. So P1 is equal to, so we have P squared over 2m is equal to 4 joules. So we multiply by 2m to bring that over, and then we take the square root. So P1 is equal to the square root of 8 joules times meters, okay? No, not meters, times mass, times whatever the mass of the particle is. So we've got 8m. I'll just take the units out of there and just say it's some scalar value. So P1 is equal to 8m, so 8m, P2, P3, and P4 equal 0. Now, let's say I let this molecule collide with these, and I take some later time, okay? At some later time, P1, and then these are x, this is still x1. The position could change, but by x1, I just mean the position associated with this first particle. x1 here may not equal x1 here. Does that make sense what I'm saying there? Okay, great. So then we still have P2, x2, P3, x3, and P4, x4. At some later time, I could have it that through collisions and interactions, elastic collisions, these particles, they share energy and momentum. And why do they do that? Because of conservation of momentum. If this one collides with this one, it's going to give some of its energy, kinetic energy, to that particle, and it's not going to be at 0 anymore. And after a certain amount of time, all of these particles, particle 1, particle 2, and particle 3, they're all going to be equal. P1 equals 2 joules, or we could say it in terms of 2m actually. So P1 equals 2m equals P2 equals P3 equals P4. In this second case, I have the same amount of energy. It's actually square root of 8m. So it's going to be, so square root of 8m divided by 4, square root of 8m divided by 4. P1 equals square root of 8m divided by 4 equals P2 equals P3 equals P4. So the total energy of my systems are the same, 4 joules. So 4 joules is the same, but the energy distribution is different. This one has all the energy, and these other ones have no kinetic energy. In this one, they all have the same kinetic energy. If I let this system go about and I maintain conservation of energy so that no energy is lost in these collisions, and I ignore any energy lost due to friction, so I say this system is frictionless, after a certain amount of time, this system will not change. It will always stay so that P1 equals P2 equals P3 equals P4. And so the distribution of momentums, the momentums are the same, and thus the kinetic energies of all of these particles are the same after some delta t has elapsed. Whereas in the beginning, all of the kinetic energy was held in just one of my particles. That's the irreversibility part. Once the system gets going, it will never go back to a situation where all the energy is again held by one of the molecules. It could, but it never does because it's improbable. And so the entropy of these systems is different. And this system is a higher entropy state. This is a lower entropy state. The entropy is different, even though the energies are the same. Okay? So we characterize, in this case, they use 7 molecules. And they do the same idea. In case 1, only one gas molecule is moving, the rest aren't moving. And in case 2, all the gas molecules are moving more or less at the same velocity. So, and the same velocity means same momentum, because we assume that all the masses are the same. Yes, question? Because what it is this particle has more energy here than it does here. Now, all of the momentum that was here is spread out evenly. The magnitude of the momentum is spread out evenly amongst these 4 particles. Yeah, sorry about that. Yes. Each one, so we divide that by 4, in other words, yes. Or, yeah, we divide that, so it's like 16 then, maybe. Okay, yeah, sorry. So that's a little bit of an error. Yes, so basically what it is the momentum of P1, this gets split by 4, so it's 16. Great catch. Okay, so we divide that by 4. Now they're split up evenly at the later stage. So the energies are the same, it's just that each one has less momentum than it had before, and they're all split evenly. Okay, great. Any more questions about that point? Okay, great catch. Okay, so it's distributed evenly, and in system A, the molecule will collide with stationary molecules and share momentum with them. And in case B, all the moving molecules continue to share momentum. So the key point here is that in this case, only one of the molecules is moving and holds all of the energy. But by the rules of physics and conservation of energy, as this system progresses, it must give a portion of its energy to all of the other participants. And after a certain amount of time, all of the other participants have the same amount of energy, and it's all distributed evenly. So this increase in entropy has to do with sharing of energy and energy being distributed more evenly across the particles. That's the first basic pass of entropy, of understanding how entropy works. But it's important to note that conservation of energy and conservation of momentum hold equally well for both systems. So actually, the irreversibility is sort of a natural consequence of us having these conservation rules. The conservation rules unexpectedly give rise to this in a subtle way. Okay, so both cases involve the same physics, but since we aren't worried about direction, the collisions in B just involve the same quantity of energy shared by the molecules. Okay, so we see energy is shared equally among the constituents in the system until the energy is distributed as evenly as possible. Once we have an even distribution of energy across all the particles in the system, we have a situation where the time evolution stops. By what I mean by time evolution is, it doesn't mean that these things stop sharing energy. It just means that any significant changes in the system stop when we look at the magnitude. Now, will there be changes to this quantity if I look at it as a vector? Yes. When these two come together and they're elastic, let's say they equally have equal momentums, when they leave with opposite momentums that they came in with. But since the energy doesn't care about the direction, since it's p squared, their net kinetic energy for two equally moving particles comes out the same as it was before. And that's what we mean by the time evolution stops. The energy, average energy between these particles no longer changes like it did in the beginning. Because it takes a while, right? It doesn't get distributed evenly when the first collision happens, when P1 hits P3. It takes more time than that and more collisions for them to all reach some equality there. But when it does, the time evolution stops, and the distribution is not reversible in general. The system won't naturally go back to one where one particle held all the kinetic energy. The laws of conservation of momentum prevent that from happening as a natural process. Thus, the process where kinetic energy is shared among particles with differing starting kinetic energies is irreversible. So, although the individual collisions are reversible, the dispersal of energy is an irreversible process. All the thermal interactions involve this spreading of energy. So now that we know that, we can say, okay, when an object is hot, it has some sort of heat. It gives off, there's collisions that occur with the object and the molecules surrounding it. So if I have colder air, and the colder air surrounds a warm body, there's collisions between the cold air molecules and my body until my body reaches the same temperature as the surrounding air, and which will happen if enough time passes, depending upon the situation. And there's things I can do to conserve energy, like wearing coats and clothing, that slows that process down. That's an insulation process. And now you know why wearing clothes is helpful. Because you wear clothes, you form a barrier between yourself and that outside environment. And so the process of sharing energy with your environment is hindered. So there's the entropy understanding of why you have to wear clothing, and the colder it is outside, the more clothing you have to wear. It's not really just from conservation of energy, it's also from entropy. And so all thermal interactions involve this spreading of energy. And once the distribution of energy is evenly spread, on average, it will not change across the many particles of the system. So what that means is that nothing crazy is going to happen where we have a bunch of cold air, but one of the molecules reaches a temperature where it can do something crazy like vaporize or something. Like we don't see spontaneous crazy things happening in a system where the energy is uniformly spread out. So that creates a lot of stability in the universe. So this is a very helpful thing. It helps keep our Earth-Sun gravitational system in thermal equilibrium. It helps keep things staying the same for a long period of time once they reach this sort of nice temperature. That's why the temperature of Pluto doesn't change drastically once it's at some distance from the sun. It kind of reaches that corresponding temperature. Okay, so how energy is concentrated is not spontaneous. So if we concentrate energy in a certain region, it's not spontaneous. It's not natural for energy to just suddenly be distributed in one or a few particles in a many particle system. So an example is, I could do something to this system to actually reduce the entropy of the system. I could go in with a pair of tweezers or some other instrument, and I could grab these particles and bring them back to a stop. I could put a barrier here and separate this particle from the rest and bring these other ones to a halt. And then for this system, my entropy would be reduced. But the amount of work that it took for me to do that would itself introduce entropy into this larger system of me going in and changing the system. So for a subsystem, the entropy can reverse, but it takes work to do that. So that's the connection between work and entropy. There's a connection there as well, which we will explore more next class. All right, have a good weekend.